we are going to learn this important part here, that is address translation. So we know what do we mean by address translation. When we are converting our virtual address into our physical address, it is called as address translation. So in a system with virtual memory, program is using what virtual address to access this large data. So what happened is that every program thinks that it has this huge data, that is this address, virtual address completely is there, but actually it uses virtual address, and address is actually an imaginary large memory. The program never directly deals with this physical RAM. It only has this imaginary virtual address, and the program will think that it has that many huge memory in it, but actually it has to take it from the RAM, but it has no contact with this physical RAM. So what happened is that there is translation, that this virtual address has to be converted into physical address. So when I'm converting this virtual address to this physical address, there would be a page a page table. If in that page, you have to understand why I'm converting that. Maybe the page can be present in the RAM, maybe the page cannot be present in the RAM, it can be present in the hard drive. If I found out that this physical address is present in the RAM, then it is there. Otherwise, that page is not present in the RAM and it is present in the hard drive, means what? Page fault is occurring. So first you have to understand our virtual memory and the physical memory is divided into some pages, and these pages have their page size. This is a fundamental unit of transfer between the hard drive, RAM and the address space, just like cache blocks. This is this pages is just like what? Cache blocks. So here the most significant bit that is in our virtual memory address, there would be some most significant bit of this virtual or physical address would specify what? The virtual or physical page number. Okay, so these pages has numbers, page 0, page 1, page 2, page 3, like that numbers is there. Now this numbers you can find out using the most significant bit, that is the most significant bit of the virtual address would define the virtual page number, and the most significant bit in the physical address would specify the physical page number. So in any address, if you take the upper bits that is there would which actually identify which page you have, we are basically referring to, like page ID. And the least significant bit is what? Page offset. So the most significant bit in an address is the page number, and the least significant is the page offset. This would specify the word within the page. This is the page offset. Page offset would decide, okay, where in this page is that word is present. That is decided by page offset. So an address is divided into two parts. You have page number and you have page offset. Page number is a upper bit, the most significant bit would define the page number, that is in which page, and where in the page is decided by the page offset, that is the lower bit. So how do we understand that? Okay, you have to understand this. Let's say this is just an example that you have to understand. Okay, it said that okay, it is saying that this virtual memory has this many capacity, that is 2 GIB means GIB. I will show you one thing that I wanted to say. Okay, GIB means it is 2 raised to 30, MIB is 2 raised to 20, KIB is 2 raised to 10. This you have to understand. Now, if the virtual memory has a size of 2 GIB means 2 raised 2 into 2 raised to 30, that is 2 raised to 31. That means there are 2 raised to 31, right? That means there are total 31 address bits. That is total virtual memory address bits are 31. Total there are 31 bits. Now, if the physical memory capacity is given as 120 MIB means MIB I told it was 2 raised to 20. 128 into 2 raised to 20. Now you know 128 means it is 2 raised to 7. So 2 raised to 7 into 2 raised to 20 would give us what? 2 raised to 27. That means for physical memory bits, there are total 27 bits in there. Now this 31 bits can be divided to what? Virtual page number and page offset. This 27 bits can be divided to again physical page number and page offset. Now in order to find, now let's say the page size also is given in the question as 4 KIB, that is 2 raised to 2 into 2 raised to 10, that is 2 raised to 12, that means 12 page offset. That means here in this 31 address bit, 12 bits are what? Offset, and in 27 12 bits are offset. The rest bits, that is 31 minus 12, that is 19, are what? Virtual page number, and 27 minus 12, that is 15, are physical page numbers. So how many virtual pages are there? This 2 raised to 31 divided by the page size. 2 raised to 12, you get 2 raised to 19. Similarly, how many physical pages are there? 2 raised to total capacity 2 raised to 27 divided by 2 raised to 12. We will get how many physical pages are there. So that means 19 bits are the virtual page number bit, and 2 raised to 50 means 15 bits are the physical page number bits. That means, I'll show you one thing. That means you can see here, if my total, it's given that we found out 31 bits are the total virtual bits. That means our virtual memory address, in our virtual memory address there are total 31 bits, and out of that we have found out that page size is 2 raised to 12. That means 12 bits are offset bits. That means least significant 12 bits are what? Offset. Rest 31 minus 12, that is 90, which you can also calculate using 2 raised to 31, that is total capacity divided by the page size 2 raised to 12. If I did this, I can get 2 raised to 19, and their bit is what? 19. So this is my virtual page number, and this is my what? Page offset. That is what it means here. Okay, I hope you have understood this. So we have understood this part.